Welcome to our panel on quantum photonics, the science of harnessing single photons for revolutionary tech like quantum computing and secure communication. For decades, this meant massive tables packed with mirrors, lenses, and lasers, powerful but bulky, expensive, and fragile. Enter the Challenger, a silicon chip, smaller than your fingernail, that can generate quantum-entangled photons using microscopic structures. This quantum light factory aims to shrink the entire lab onto a single mass-producible chip. The traditional setup is like a custom race car, hand-tuned, high-performance, but impossible to mass-produce. The chip is more like a modern car engine, reliable, consistent, and built for millions. The big question, can this tiny chip really replace the room-sized quantum lab? Today we'll compare these two worlds, how they work, their strengths and weaknesses, and which one could unlock our quantum future. We'll explore everything from photon creation to real-world reliability. This isn't just a technical debate, it's about the future of technology itself. Will quantum breakthroughs stay locked in elite labs, or will they reach everyone? Let's dive in and find out. The stage is set, tradition versus innovation. Let's get started. How do these systems actually create quantum light? In bulk optics, a powerful laser hits a special crystal, splitting photons into entangled pairs, a process called SPDC. It's flexible. Scientists can swap crystals, tweak lasers, and adjust mirrors for custom experiments. The on-chip approach uses a microring resonator. Light circulates in a tiny silicon ring, triggering a process called SFWM to create entangled photons. The chip trades hands-on flexibility for built-in precision and repeatability. Once manufactured, its properties are fixed, but it's stable and immune to room vibrations. Bulk optics is a physicist's playground, perfect for exploration and discovery. The chip is a push-button device, engineered for reliability and mass use. Both create entangled photons, but their philosophies are worlds apart. One is endlessly customizable, the other is robust and ready for the real world. The choice shapes the future of quantum technology. Let's see how they scale. Scalability is key. Can we go from one device to millions? Bulk optics setups are hand-built, slow and costly, impossible to mass-produce. Each table needs expert alignment and constant care. The chip, made with standard CMOS processes, can be produced by the thousands on a single silicon wafer. Semiconductor foundries already make billions of chips for electronics. Quantum chips can ride this wave. On a table, adding complexity means more parts, more space, and more headaches. On a chip, complexity is just a matter of design. Add more photon sources, detectors, or circuits before fabrication. Integration is the chip's superpower. Sources, detectors, and processors all on one tiny platform. Bulk optics hits a wall. Chips scale effortlessly. This is how quantum tech moves from the lab to the world. Next, let's talk about reliability. How do these systems hold up in the real world? Reliability is everything, especially outside the lab. Bulk optics setups are fragile. A tiny vibration or temperature change can ruin alignment. Constant maintenance is required, making them impractical for real-world deployment. The chip's components are etched in solid silicon. No moving parts, no misalignment. It's robust against shocks and vibrations, like a digital watch compared to a mechanical one. This stability is a game-changer for practical quantum devices. For a global quantum network or a commercial quantum computer, set and forget is essential. Chips can run for years without expert intervention. Bulk optics will always be valuable for research, but chips are built for the field. Now let's look at how these systems are manufactured. Can we mass-produce quantum devices quickly and cheaply? Bulk optic systems are hand-assembled, expensive, and unique, like custom furniture. The chip leverages automated CMOS foundries, producing thousands of identical devices with nanometer precision. Standardized processes mean costs drop as volume rises. Uniformity is crucial. Chips from the same batch perform almost identically, unlike hand-built setups. This manufacturing edge could democratize quantum tech, making it accessible to startups and even hobbyists. Just as integrated circuits brought computing to everyone, quantum chips could do the same for quantum technology. Mass production isn't just about numbers. It's about opening the door to innovation. Next, let's tackle a hidden challenge: temperature. How do these systems handle the heat? Temperature is a silent enemy for quantum systems. In bulk optics, even a tiny temperature change can misalign mirrors and ruin experiments. Labs need expensive climate control. Chips are also sensitive, but in a different way. Silicon's properties shift with temperature, affecting performance. The solution? Integrate tiny heaters and sensors directly onto the chip for precise local temperature control. This is far more efficient than stabilizing an entire room. Chips can maintain optimal performance even in changing environments, outdoors or in variable conditions. Bulk optics can't compete with this level of adaptability. On-chip thermal control is another reason chips are ready for the real world. Integration solves problems that are intractable at the macro scale. Now, which path leads to the quantum future? So, which approach will shape the future? The on-chip quantum light factory offers scalability, integration, stability, and mass production, key for real-world quantum tech. It leverages existing manufacturing, packs thousands of components into tiny spaces, and is robust enough for everyday use. Challenges remain. Photon quality and integration of different materials are still being improved. Bulk optics won't disappear. It's still the gold standard for research and discovery. Think of it as Formula One, where new ideas are born before they're engineered for the masses. The future isn't one or the other, it's both. Bulk optics will push science forward. Chips will bring quantum tech to the world. For practical quantum computers, networks, and sensors, chips are the clear frontrunner. The quantum revolution won't happen on a lab table, it will happen on a chip. The path is clear integration, scalability, and real-world impact. The future of quantum light is in your pocket.